All right, let's dive right in. We're going to talk about one of the most powerful and, honestly, most widely used algorithms in all of machine learning. A lot of data scientists consider it their secret weapon. It's called the random forest.
And look, I'm not kidding when I say this thing is everywhere. From scrappy startups to massive Fortune 500 companies, if they're working with structured data, your classic spreadsheets and databases, there's a really good chance they're using a random forest. Its versatility is what makes it such a workhorse in the AI world.
And its impact is huge. We're talking about finance, where it's sniffing out fraud. In healthcare, it's helping to diagnose diseases. For retail, it's predicting what you're going to buy next. It's even a beast in cybersecurity, flagging threats and powering thousands of decisions every single second.
So, to really get why a forest is so powerful, we first have to understand the single tree. Because a single decision tree, well, it's simple, it's easy to understand, but it's got some pretty serious flaws.
The biggest problem with a single tree is that it tends to overfit. It basically just memorizes the data you show it instead of learning the actual patterns. Think of it like a student who crams for a test. They can answer the exact questions they studied, but they're lost on anything new. This also means it's super unstable. A tiny change in the data can result in a totally different tree, which makes its predictions pretty erratic. And these are the exact issues the random forest was built to solve.
And this is where the genius of the idea comes in. The solution is just beautiful. Why rely on one flawed decision maker? Instead, what if you created a whole crowd of them and then just listened to their collective wisdom?
This quote just nails it. It's the whole idea behind what we call ensemble learning. You take hundreds of these simple, kind of weak trees, and when you combine them, you get something that is incredibly strong, stable, and way more accurate. It's the perfect example of the whole being so much greater than the sum of its parts. So, at its heart, a random forest is an ensemble method. It doesn't build just one tree, it builds hundreds, sometimes thousands of them. And then it cleverly brings all their individual predictions together to create one final answer that's way more reliable than any single tree could ever hope to be.
So, how does this forest actually make a final call? Well, it's pretty democratic. If you're doing a classification task, like is this email spam or not spam, every tree gets a vote and the majority wins. Simple as that. If you're doing a regression task, say predicting the price of a house, it just takes the average prediction from all the different trees. It's an elegant, super effective system. Okay, but wait a second. How do you stop the forest from just being a bunch of identical trees all making the same mistakes? Good question. The answer lies in two brilliant techniques that introduce randomness. This right here, this is the secret sauce of the algorithm. The first pillar is a cool idea called bootstrapping. So imagine your data is a big textbook. Instead of giving every tree the exact same book to study, you give each one a slightly different copy. You do this by randomly picking pages to include, but you do it with replacement. That means some pages might show up a few times, and some might not show up at all. The result? Every tree gets a slightly unique perspective, which creates a really diverse forest. And the second pillar is random feature selection. This is just as critical. At every single decision point, every fork in the road for a tree, it's only allowed to look at a small, random handful of the information. So instead of looking at all 10 customer details, maybe it only gets to consider age and income. This forces each tree to explore different ways to make a decision and stops one super powerful feature from just dominating every single tree.
So let's put that all together. Here's how it works, step by step. First, you bootstrap your data into lots of different samples. Then, you build one tree for each of those samples. But as you build, you randomize at every split but only looking at a subset of features. Finally, you let all the trees vote or average their answers to get one final, super solid prediction. That's the whole process.
Okay, so we've gone to all this trouble to build this diverse forest of decision makers. What's the payoff? Well, it's about more than just getting a single accurate prediction. The real benefits are actually much, much deeper.
Now, have a look at this number, 36%. What do you think that represents? An error rate, maybe? Nope. It's actually one of the cleverest and most efficient parts of the whole random forest algorithm.
This is what it is, the out-of-bag data. Remember that bootstrapping process? Well, it turns out that on average, each tree is built without ever seeing about a third of the original data. And the algorithm brilliantly uses this leftover data, this out-of-bag sample, as a free built-in test set to check its own accuracy while it trains. It's like getting a free quality check without any extra work. So the advantages really stack up. You get high accuracy, it's great at resisting that overfitting problem we talked about, and it's practical. It handles missing data pretty well, and you don't have to do a bunch of tedious data prep like feature scaling. But honestly, its most valuable gift is the insight it gives you.
And that's something called feature importance. The random forest doesn't just give you an answer, it tells you why it gave you that answer. It actually ranks which pieces of information were the most important for making its predictions. For a business, this is pure gold. It helps you answer questions like, what's really driving our customers away? Or which of these factory sensors actually predicts a failure? It gives you real, actionable insights.
Now, random forest is an absolute superstar, but it's important to know where it fits in the big picture. It's not the perfect tool for every single job, so let's see where it sits in the broader AI world.
When you look at the landscape, it becomes pretty clear. For structured, tabular data, your classic rows and columns, random forest is the king of being robust and easy to use. Now, something like gradient boosting might squeeze out a tiny bit more accuracy, but it's often way more complicated to tune. And when you get to unstructured data, like images or text, that's really where neural networks are the champs. The key is picking the right tool for the job.
And of course, let's be real, no algorithm is perfect. There are always trade-offs. A forest with 500 trees is obviously way harder to understand than just one single tree. It can also be a bit slower and take up more memory to train, especially as you add more and more trees. That's just the price you pay for all that accuracy and stability.
So if you remember just one thing from all this, let it be this. The random forest algorithm is just a beautiful example of the wisdom of the crowd. It takes hundreds of simple, even weak little decision makers, adds just the right amount of randomness, and combines them to create a single model that is incredibly powerful, reliable, and just so versatile.
And that kind of leaves us with one final thought. Now that you get how it works, how it breaks down a huge, complex decision into a whole bunch of simpler ones, think about the world around you. What's a complex problem, maybe at your job or just in your life, that you'd want to solve with your own forest of decisions?